Good to see you all. My name is Alexei Poznikov. I'm co-organizer of the BayLearn, and I'm with the Sidewalk Labs, and it's an alphabet company, and we build cities. And nowadays, it really takes a lot of machine learning engineers to build cities, and that's exciting. So if you're interested to talk about it, you're welcome. And when we pour these technologies into like everything we do in our everyday life, in cities, in cars, in streets, it becomes really important to make sure that things will work as expected and will be robust against normal situations, but also attacks. And this topic of adversarial machine learning becomes really, really key. And we're very excited that we got a chance to learn from the best. And with that, I would like to introduce you our last keynote speaker for today. It's Ian Goodfellow. He is very well known in the field. Currently, Ian is a staff research scientist in the Google Brain, where he leads the team working on these problems. He's been at the University of Stanford, University of Montreal, OpenAI. He is a lead author of the very good book that is available to you online on deep learning. So please take your time to learn from that as well as from today's talk. Thank you very much. It's up to you.
Thank you. Good afternoon. Thank you for coming. Can everybody hear me okay in the back? Mic's loud enough? Okay, great. So I will be telling you all about the dark arts and how to defend against them. Specifically, I'll be telling you all the things that people can do to make machine learning go wrong intentionally in potentially dangerous ways. And I'll tell you about the state of the art in research to defend against these kinds of attacks that people can mount to interfere with machine learning. I'm giving you an overview of a field. I'm not just telling you about my own research. Some of this work is mine, some of this work is that of my collaborators, but probably the majority of what I'll tell you about today is actually other people's work. If you go to www.iangoodfellow.com, you can get the slides for this presentation, and the line that's underlined right there is a hyperlink to a Google Doc with a bibliography saying all the different papers that I synthesized to make this talk. In order to make the focus of the talk be on the concepts rather than on which papers introduced each of the concepts, I'm not going to tell you exactly which paper each slide is drawing from necessarily, but if you look at the bibliography, you can find it. If we look at the pipeline that we use for a machine learning algorithm, there are several different stages to this pipeline. And from the point of view of someone who's interested in security, we can think about ways that attackers can strike each of these different stages. I'll use the same notation throughout the talk. Basically, it's the same notation as in the deep learning book or Andrew Ng's lecture notes, if you're familiar with either of those. I'm going to use a capital letter X to represent the training data, and then I'm going to use the vector theta to represent parameters learned by an algorithm that we apply to that training data. And then at test time, I'll use a lowercase letter x to represent a new input that this system processes using the parameters that it learned. Applying the parameters theta to the test input x, we get some kind of test output, maybe a prediction of which category or class x belongs to as our test output y hat. In some cases, like reinforcement learning, the test output will be more complicated than just a selection of a class. But as far as the security concerns go, the division of the pipeline is still relatively similar. You can interfere at training time, you can interfere at test time. One of the main concerns that we have is making sure that the privacy of the training data is preserved. You can imagine that if we use a little white queen to represent one player in a game and a little black queen from chess to represent another player in a game, you can imagine two players competing, one trying to learn useful functions from data and publish information about those functions, and another player trying to study the published results and reveal private information about the training set. So here we begin with a training set. We would like to study it and learn something useful that we encode in the parameters theta of a model. This might be something like private medical data that we then use to learn to make a diagnostic model. And maybe we'd like to open source that diagnostic model and publish it so that doctors around the world can use it to diagnose their patients. It would be unfortunate if someone malicious could examine this trained diagnostic model and recover specific information about individual people who were in the training set, especially if any of that information was personally identifiable. And a lot of the time, information can be personally identifiable, even when you think you might have taken some steps to reduce its identifiability. The main way that we combat this kind of attack is using what's called differential privacy. Differential privacy is a concept that was developed much earlier for protecting accesses to databases, but we can also apply it to machine learning. The basic idea is hinging on the word differential. We're looking at the difference between what happens when we train on two different data sets. I think most people in the audience will hear differential and assume it's about derivatives. It's actually about differences between two different runs of a training algorithm. One of these runs happens on a training set with all of the users in the data set. The other one happens on a data set where one user has been removed. If you can prove that the outcome of the training process is indistinguishable between these two cases, then we know that this one user who is in one of the training sets and out of the other training set had no real effect on what the classifier learns. It means that the machine learning model has learned general patterns that could be useful, for example, to diagnose a disease, without memorizing private information about the individual user. To do this, of course, the machine learning algorithm has to be somewhat randomized. There has to be a little bit of uncertainty about which parameters it learns for a specific training set. Otherwise, you could invert the process and figure out exactly which training set it had looked at. But by introducing some randomness, we can guarantee that the machine learning algorithm will produce statistically indistinguishable outcomes, regardless of whether any individual user is in the training set. At Google Brain, in collaboration with OpenAI, we wrote a paper about a technique that we call private aggregation of teacher ensembles. The basic idea is that we can guarantee differential privacy by splitting the training data into more than one disjoint group. If a different model trained on each of these disjoint groups learns the same pattern, then we know that it's safe to publish that pattern. That's the basic idea behind this pate algorithm. At the end of the process, we actually distill the knowledge into the different teachers into a single student network. So rather than publishing the individual teachers, each one of which may have memorized something about specific users in the training set, we can publish the student network who has learned a privatized summary of the general patterns that the teachers have found that they all agree on with each other. Another important category of security attacks that we could see in machine learning is called training set poisoning. Here, the black queen, representing the malicious player in this two-player game, is able to interfere with the training set, represented by the fact that they've turned the capital X, representing our training data, red. This is called poisoning because the effect on that training set is then consumed by the training process and affects everything that comes afterward. Even though the attacker can't directly affect the parameters that the model learns, the training set can affect those parameters. And then the change in those parameters changes the output that the model produces at the end of the day. So imagine that we train a classifier that's designed to recognize malware. We usually train these classifiers by finding examples of malware in the wild and adding them to our training set. If an attacker were particularly skilled at training set poisoning, they could make a piece of decoy malware that they release into the wild, intending for us to catch it and add it to our training set, if they knew that it would then affect the parameters theta that we learn in a way that would allow some later real piece of malware to bypass our filter. By injecting something that they control into our training set, they could actually control the way that we predict the output value for specific test inputs later on. A recent paper that demonstrates training set poisoning at relatively large scale is this paper from Stanford, where they show that if they add this image of a dog with some adversarially calculated pattern added to it, and they label it as a fish in the training set, then they can change the test set label of all 5 of the dogs shown in the lower row of this slide. Each of these dogs was correctly classified as a dog before the addition of this poisoned training example. After the addition of the poisoned training example, they are all recognized as being fish. You could imagine a similar thing could be done with a malware binary that could cause several malicious binaries that would be recognized as dangerous to flip and be recognized as safe and get through the filter. Adversarial examples are another kind of machine learning security concern. In this case, the attacker is able to interfere with the input at test time. And rather than presenting a normal input, they present an input that has been optimized in order to fool the model into producing an incorrect output. Another version of security and privacy concerns that come up in machine learning is called model theft. Model theft is when a malicious adversary is able to observe inputs that are sent to the model at test time and also to observe the output of the model. If they can observe a lot of these input and output pairs, they can essentially build their own training set and train their own machine learning model that imitates the behavior of the targeted model. There are a few different reasons that you may not want a malicious adversary to be able to do this. One is, as I just mentioned, you can recover unwanted information about the training set if you're able to recover the parameters. So earlier when I was describing differential privacy and how we would want to make sure that an adversary could not analyze the parameters of the model, we need to also keep in mind that while we may not explicitly publish the parameters of the model, we publish the model's predictions. And if those can be used to reverse engineer the parameters, they can be used to, they can also be used to reverse engineer the training set. So model theft has implications for privacy. Also, once the attacker knows exactly how the model works, they can make better adversarial examples. They can make maliciously optimized inputs that are designed to fool the model. And after they've stolen the model and reverse engineered it, they know exactly how the model behaves, so they can actually test their adversarial examples before they deploy them and be confident that they're going to cause the model to make a mistake. One thing that we've started to see is that very advanced models can infer information that we usually think of as private. One study found that a machine learning model that is able to see a user's likes on social media, given enough likes, can actually predict attributes of that user's personality better than their friends, coworkers, or family members can do. This reminds me a little bit of Sherlock Holmes. I've put a little graphic representing Sherlock on the left. If you read the Sherlock Holmes stories, there's several instances of encounters where someone comes to talk to Sherlock Holmes and he guesses their name and guesses that they're having some conflict with their spouse or something like that. And his client is always surprised that Sherlock already knows their problem before they've told it to him. And then he explains how he was able to deduce their problem by little clues like marks on their shoes and so on. Machine learning is kind of like the modern day version of Sherlock Holmes. It is able to infer things that we don't realize we're broadcasting to the world because it is able to recognize patterns much better than the average person. And so in some cases, while we may technically be preserving privacy in terms of what we publish, our machine learning algorithms may be able to infer more than the information we think we're able to publish. Another security concern we've seen is called automated crowdturfing. This is where machine learning is actually used to mount an attack. For example, in this paper, machine learning was used to generate several fake Yelp reviews. The Yelp reviews are designed to look realistic, as if they were written by real human users. But you could imagine that a malicious restaurant could use a generative model to flood Yelp with positive reviews for their restaurant that trick people into eating there, even though it's mediocre. You could also imagine flooding your competitors with negative reviews that appear to be realistic. Fake news is fortunately not yet really something that happens with machine learning as far as we know, but a lot of the techniques that we have today have raised concern that they could be used to generate fake photographic or audio or video evidence of events that have never happened in the future. If you go to futureoffakenews.com, there's this fake video of a speech by Obama that never happened. The man in the upper left is using Obama's face as a neural puppet. As the man on the upper left speaks, Obama's face matches his facial expression. And the words that Obama has been saying in the audio are also produced by a machine learning model. This seems to suggest that in the future, we won't be able to rely on media evidence to tell us which events have actually occurred anymore, or we will need to develop much better machine learning forensics to detect tampering with these kinds of evidence. Machine learning models have also been used for password guessing. Essentially, users cannot really be trusted to generate random passwords very well. You should use a password generator and enable two-factor authentication for any important account that you want to secure. Machine learning models are able to generate random passwords that resemble the kind of passwords that human users create. They're able to generate lists of passwords longer than the ones that are already available on the web for attackers to use, longer than the ones that have been scraped from compromised users' accounts. And when you use this additional lengthened list provided by the machine learning model, you can break into accounts that you would not be able to break into otherwise. Some people have even suggested that AI may have concerns for geopolitics in general. Elon Musk and Vladimir Putin have both said that in the future, AI will actually be used for conflict between states. So a lot of these concerns about machine learning security could, in the future, have concerns for national security. And a lot of what motivates me in my research is to make sure that we make it harder to attack than to defend, so that machine learning can promote stability of interactions between different entities who may want to have a conflict. Most of the remainder of the talk will be a deep dive into adversarial examples, the aspect of machine learning security that I've spent most of my own time studying. Adversarial examples are inputs that cause machine learning models to make a mistake. And nobody studied them until very recently because until very recently, machine learning models made mistakes all the time. In 2011, if you had come to me and said, hey, Ian, I've got an example that makes a classifier produce the wrong output, I would say, good for you. I have about 5,000 of those in my terminal right now. But since about 2013, we've started to see a lot of different tasks like object detection, object recognition, face recognition, reading obfuscated text for CAPTCHAs, reading photos of text, and so on, where machine learning algorithms have actually matched or exceeded human performance. In some cases, there's kind of a big asterisk, like on ImageNet, humans probably are better at computer vision than machine learning models. On the ImageNet dataset, we test both humans and machines by asking them to recognize 1,000 different categories. And there's a lot of South American rainforest animals that most of us are not very good at recognizing because we've never heard of them before. But the machine learning algorithm beats us because it has a training set with 1,000 images of every category. But modular those asterisks, machine learning works pretty well now. And so it's become interesting to study the cases where it fails. Adversarial examples are one of the cases where machine learning fails very consistently. In this particular example here, I've started with an image of a panda on the left, and I've added a carefully calculated vector in the middle to this image. I've scaled down the magnitude of the vector that I added to the point where you can just basically not detect the perturbation. If you represent this image in 32-bit floating point, the perturbation is there. If you represent it with 8-bit ints, it gets rounded down to nothing. So as you look at this image on the projector, the panda on the left and the panda on the right are actually exactly the same as each other. For the inception convolutional network used to recognize this image, they are in fact different because the network accepts inputs in float32 format. The image on the left is recognized as being a panda with about 70% confidence. The image on the right is incorrectly recognized as being a gibbon with about 99.9% confidence. So not only have we made the model make a mistake, we've actually made it have higher confidence when it's wrong than when it was right. This phenomenon for neural nets was discovered back sometime before 2013, first published in 2013. I was on a team that published it with Christian Szegedy being the first person who really noticed this. Independently, Battista Biggio also noticed this for things like MNIST classifiers and published that in the same year. So there were two groups independently studying this phenomenon. In 2014, I developed a faster, cheaper way of making these fooling images. And that's the kind that I've actually shown on this slide here. So that's done in a closed form formula. There's no iterative optimization required to turn this panda into a gibbon. And on these kinds of images, machine learning models, in many cases, get essentially 100% accuracy. Every now and then your optimizer might fail, but it's really just noise. When Christian first noticed this effect, he was actually trying to understand how convolutional networks work. He wasn't trying to break them. He was thinking, what would happen if I ran gradient ascent on the log probability of the airplane class? And I've repeated the same kind of experiment he did here. Each of these little grids is an animation. You read it left to right, top to bottom, like reading words on the page of a book. And every different frame in the animation is another step of gradient ascent. At the start, we have an image from the CFAR10 test set. And at the lower right, we have an image that the convolutional net believes is an airplane with very high probability. Not that it's just barely an airplane, it's 90% confident that it's an airplane. If you're anything like me, you look at these and think nothing at all changed. You must have a bug in your gradient ascent algorithm. And indeed, the first time I ran this, I took the images and I compared them in NumPy and verified that there really was a diff. It took a long time to persuade myself that this is really happening. But essentially, if you go and you optimize inputs to neural nets, you can change the class while barely making any change at all. It turns out the same things happen to linear models as well. This is a problem for most of machine learning, not just for neural nets. In this case, I have a 10-class softmax regression model. Softmax regression is a shallow model. It can't scale to large and complicated data sets. So here I've just run it on the MNIST data set. And I begin with an image of a 9. As you follow the animation left to right, top to bottom, I maximize the log probability of all 10 different MNIST classes. Everywhere that you see a yellow box, the model has changed its mind and decided that it's the next class with high probability. I think about 90% probability was the threshold that I used for the yellow box. And then once I have hit a class, I move on to the next class. So the first yellow box in the top row, that's the 0 class. In the second row, that's the 1 class. And then as you move left to right, top to bottom, I visit all the other classes until at the bottom right, we're back to the 9 class. The only image that I would say is correctly classified here is the image of the 9 at the bottom right. And the only reason that that is correctly classified is that we started the whole process with a 9. So we managed to use gradient descent to visit all of the different classes without ever really meaningfully changing the input. And this isn't something resulting from the model being extremely complicated. This is just a linear model. So adversarial examples are a pretty salient phenomenon, and they happen for lots of different kinds of machine learning models, even very simple ones. So what's actually going on here? When Christian and my other co-authors and I first started studying adversarial examples, we all kind of assumed that they were an instance of overfitting in some sense. So the overfitting story I've tried to illustrate with a training set containing a line of blue X's and a curve of green O's. The blue X's are one class, the green O's are another class, and then I've drawn little blobs of blue or green probability mass showing where a classifier might believe test set examples from each of those classes would appear. According to the overfitting story, we managed to put a blob of blue mass around the training set blue X's, and we managed to put a blob of green mass around training set O's. But then we also just throw out some random blobs of probability mass that we can't really control because the model class is so big and complicated, and our training process is so essentially random because we're choosing from a very big hypothesis space of functions. According to this story, some of those random blobs would have adversarial examples in them. So I've drawn a red X and a blob of green mass that's much closer to training set X's than it is to training set O's. And I've drawn a red O and a blob of blue mass that you could imagine maybe should be classified as, I've drawn a red O that would be classified as an X because it's in a blue blob, but it's closer to the O's, so it should probably be classified as an O. Well, it seems like a reasonable story. If we go out and start gathering some evidence for it, some things you might do are we might try running the same adversarial example through several different models. If we really are just suffering from bad luck and every model learns in a more or less random function, a more or less random process when it chooses a function from hypothesis space, we would expect different models to overfit differently and suffer from different adversarial examples. That's not actually what we found. We found that the same adversarial example fools several different models. That led me to think that something different might be going on, that we might actually be seeing adversarial examples coming from the model being too linear. Here I've drawn the same kind of training set structure again, but with a linear classifier dividing up space. What we see here is you can still draw adversarial examples even for this very simple decision boundary. In particular, modern deep networks are very piecewise linear. And we do this because we've actually designed the hidden units of the networks to be linear in order to make them easier to train. For example, rectified linear units are essentially piecewise linear with two pieces. But what happens when you actually make a network out of them? If you're like me, I always assumed that the network structure was like combining a bunch of Lego blocks to make a really complicated shape that didn't look very much like a piecewise linear function anymore. So I tried making linear cross sections moving in a straight line through image space and plotting the outputs of the neural net. On the left, I show you different images that lie along a ray in Rn. And on the right, I show you a plot tracing out the unnormalized log probabilities produced by the model. These are the values right before the softmax at the end. And every different color of curve is a different class for a CFAR10 classifier. You can see that the top probability in most places is the frog class. This happens anytime that we've strayed very far from the training data. On the left side of the curve, the frog class is high when we've subtracted this perturbation off of the input. And on the right side of the curve, the frog class is high when we've added this perturbation on to the input. The only place where you actually get the right class, where the automobile curve comes up higher, is in the center of the plot where there's no perturbation. But as we move further out, the model extrapolates in a basically linear fashion. So it seems like the adversary is able to exploit this linear behavior of the model. They know that if they make a small change locally and they get a small response, they can make a very large change in the same direction and they'll get a proportionately larger response. So they can actually predict where they should go looking to get an input that looks like a frog. One comment I should make really quick is I'm saying that neural nets are very linear as a function of their input. If you look at what a ReLU net looks like as a function of its input, you basically have a bunch of matrices multiplied together with some ReLUs gating them. You can represent those ReLUs locally as being diagonal matrices with zeros or ones on the diagonal. If you look at neural nets as a function of their parameters, they really are more nonlinear. There's a paper by Andrew Sachs called Solutions to the Exact Dynamics of Learning, where he shows that even a neural net with no nonlinear hidden units actually has a very nonlinear mapping from weights to cost function values, and that's sufficient to describe a lot of the behavior we see when we train neural nets. But for an adversary who wants to find malicious inputs, they're dealing with a different mapping. They're dealing with a mapping from inputs to outputs. And that mapping turns out to be much simpler than the mapping from parameters to outputs. If we look at different classes, we see that they're actually very close in L2 distance from each other. In the top row here, I show the nearest MNIST3 and the nearest MNIST7, and I show the difference between them. The difference between them has an L2 norm of 3.96. If instead I make a random perturbation with that same norm, and apply that perturbation in the middle row, we get a bunch of noise added to the 3, but we can still definitely recognize it. So small perturbations per pixel are large enough in L2 distance to travel all the way between different classes. And that's part of what's going on with adversarial examples. If we change a lot of pixels, all those little tiny changes can each vote for a specific class, and if they coordinate their efforts to all vote for the same class, a lot of those little tiny votes can add up to one very big vote. When we construct adversarial examples, we want to make sure that we don't actually accidentally change the true class. If we loaded an image of a panda and then we turned it into a gibbon, it would be fair for the model to say it's a gibbon. We want to make sure that we actually keep the class of the object the same from the start to the finish. So a lot of the time, because these L2 constraints need to be really big to make sure we don't change the class, instead we'll use L infinity constraints. Specifically, we say no pixel can change more than some small amount epsilon. And that makes sure that we can't do things like erase the white ink of an MNIST digit. And we know that whatever perturbation we make will leave the same object in the image after we've applied the perturbation. One very fast way that we can make adversarial examples is by applying this observation that neural nets are very linear as a function of their input, and by applying this requirement that no pixel should change by more than epsilon. The observation that the neural net is linear tells us that we can get away with making a Taylor series approximation of the cost that the neural net pays when it classifies the input. So we essentially linearize the cost around the current input, and then we maximize that approximate cost subject to this constraint that no pixel should change by more than some amount epsilon. That gives us a very fast rule that we can apply. We just take the gradient of the cost with respect to the input. We take the sign of the gradient at each pixel, and we add epsilon times that sign of the gradient to the input. So the sign is basically telling us, do we hurt the model when we increase this pixel or decrease this pixel? If it hurts the model to increase the pixel, we add epsilon to the pixel. If it hurts the model to decrease the pixel, we subtract epsilon off of the pixel. It's a very straightforward rule, and unless you've intentionally designed your model to resist this kind of attack, it will actually fool most machine learning models very reliably. If we then make maps of how adversarial examples are spread throughout space, we can start to answer some basic questions like, are adversarial examples rare little points that you have to search for very carefully, or do they live in very dense spaces where you can wander around in that space and find arbitrarily many adversarial examples? Our maps show us that actually they live in these dense spaces that look a lot like half spaces when we make two-dimensional cross-sections. So in each of these maps, every little cell is a different CIFAR10 test example. And the coordinates within that cell represent different points in image space. The very center of the cell is a clean CIFAR10 test example. As we move right from the center, we're adding an adversarial perturbation. As we move left from the center, we're subtracting off that perturbation. And then as we move up or down, we're adding noise or subtracting noise. The noise direction is there as a control so that you can see that this doesn't happen for every direction you might explore. If the correct class is produced when we run the model on a point, we label that point with a white pixel in the map. Otherwise, we have a different unique color for each of the CIFAR10 classes, and we plot the color of the incorrect class that was chosen by the model. So everywhere you see white, the model has produced the right answer. And you'll see that it's white on the left side of all of these plots, and that there's basically a vertical dividing line. As you move to the right, we see all of the other colors where the model has picked other incorrect CIFAR10 classes. So we can see that essentially any perturbation that has high dot product with the adversarial gradient will cause the model to make a mistake. We're not trying to hit a bullseye on a target that's a mile away. We just need to move in the right general direction, and we'll find a mistake. The test data happens to never move in these directions, but if we actually go looking for them intentionally, they're very easy to find. Florian Tramet and his collaborators at Stanford decided to estimate the dimensionality of these subspaces. In these plots, you can see that there's at least a two-dimensional subspace you can explore and find adversarial examples everywhere within that subspace. We found that for MNIST at least, there's around a 20-dimensional subspace that you can explore, and every convex combination of points within that subspace will be an adversarial example. And if you try to find more orthogonal directions, it's difficult to do that while still keeping high enough dot product with the gradient direction. So far, I've mostly told you about points that are very near test points, where we load an image of a real object and then we corrupt it slightly. It turns out that there's also images that are what Jeff Kloon's lab called fooling images, where they're similar to what was earlier described by Jan LeCun as rubbish class examples. The idea is they're inputs that just don't belong to any class, and yet the model thinks that they are one of the real classes. In this slide here, I've taken a CIFAR10 classifier, and I have run Gaussian noise through the classifier. Everywhere that you see a pink box, the classifier thought that the noise was something rather than nothing. Everywhere you see a yellow box, one step of the fast gradient sign method was enough to turn that noise into specifically an airplane, rather than just being something, rather than nothing. When we're concerned about this case, where we're loading garbage and we want to see whether the model thinks it's something rather than nothing, there are a few ways that you can parameterize the model. Most models we use today are parameterized with the softmax output function, so they're forced to assign non-zero probability to every class. If you have k different real classes, and you've trained a softmax model that recognizes those k classes, you might hope it would assign something close to uniform to these kinds of garbage inputs. But I found that it will consistently assign probability greater than 1/2 to one of the specific classes. Another thing you can do is you can add an 11th class. Assuming you have 10 classes, like in this example on CIFAR10, you can add an extra class to your softmax representing the class of fake things. I found that if you train it to reject Gaussian noise as being this extra garbage class, it's still easy to fool into accepting Gaussian noise that's been modified by the fast gradient sign method to look like a real class. One last thing that you can do is you can use an independent parameterization of each class. Rather than having a softmax that tells you which of k classes are present, you can have k different sigmoids that tells you the probability that each class separately is present or absent. This representation can actually say that more than one class is present simultaneously. And I've found that for Gaussian noise, that actually happens quite frequently. That you basically, it's very rare to find a Gaussian noise example that doesn't activate any of the K classes. Most of what I've shown you has been adversarial examples for image classifiers. There's also been a lot of work recently on adversarial examples for reinforcement learning. If you follow the link in these slides here, there's approximately a 6-minute video of different reinforcement learning agents playing different Atari games, and small perturbations of the pixels cause them to fail to play the game very well. I've spent a lot of time criticizing linear models and saying that deep neural nets are too linear. Well, one alternative is to use quadratic interactions in your model. If you train a shallow RBF network and you run the same animation I showed earlier with the softmax model, you can start out with a 9 and maximize the log probability of a 0, a 1, a 2, and so on, and you actually get all of the different digit classes. Unfortunately, you don't get very good classification accuracy on the clean test data compared to what you get with a deep neural net. This shallow RBF model is basically just a template matcher. So it's just steering the input toward 10 different templates that it has learned, but it isn't very good at recognizing a diverse test set. If you want to train a much deeper neural network, then that can be difficult just to get it to perform well on the train or the test set. And so we don't yet really know what happens if you have a really strong deep RBF net. But that's one potential way we could defend against adversarial examples. One thing that's particularly concerning about adversarial examples from a security point of view is that they tend to generalize both across different models and across different data sets. You can train 2 models on 2 different subsets of the training set that don't overlap, and they'll be vulnerable to the same adversarial examples. Not 100% of the same adversarial examples, but there will be a high transfer rate between the 2 models. That also applies if you use different architectures for the model and train them on the same training data. You can even use different machine learning algorithms. Nicholas Paperno has spent a lot of time studying the transfer rate between entirely different kinds of machine learning models, like support vector machines, decision trees, ensembles containing neural nets, and other kinds of models. And some of them do have relatively low transfer between particular pairs, but there's a surprising amount where there's a very high transfer rate, even though the algorithms seem to be doing something completely different from each other. This is one of the main mechanisms that an attacker can use in practice. Essentially, the attacker starts by targeting some model that has unknown weights that they don't actually have access to. They can either train their own model on their own training set, or if they don't have a training set of their own, they can do a model theft attack by sending inputs to the target model, observing its output, and reverse engineering its parameters. After you have your own copy of the model, you can make adversarial examples that fool your model, and then send those adversarial examples back to the targeted model. So you can actually fool a remotely hosted model without ever knowing which training algorithm it's running, which architecture it is, or the value of its weights. You can also improve the chance that your adversarial examples will transfer to the target model by using an ensemble of several different models. If you can find an adversarial example that fools every member of an ensemble of 5 models, the group at Berkeley has found that in their experiments, such an attack has essentially a 100% chance of fooling a 6th model that they then deploy these adversarial examples to. A lot of people ask me if there are adversarial examples in the human brain, and the short answer is yes, we call them optical illusions. On this slide, this image is actually of concentric circles. It looks like it is spirals intertwining with each other. Even having used this slide for a few years, I still completely see them as intertwining spirals. But this isn't quite answering the question I think a lot of people have. I think a lot of people are wondering, could you actually make little tiny perturbations to every pixel of an image and make me think that a school bus is an ostrich? And we actually don't really know yet, because we don't actually have a full specification of the human visual system, so we can't run the optimizer on it directly. What we do know is that adversarial examples transfer between lots of different machine learning models, and they don't seem to transfer from machine learning models to the human visual system yet. So we know for sure that the human visual system is pretty different from our current machine learning models. We don't actually know whether it's vulnerable to this category of adversarial example or not. But it is definitely vulnerable to the kind of optical illusions that neuroscientists write about all the time. A lot of people have wondered whether adversarial examples would hold up if you took them out of the computer and tried to use them in the real world to fool a robot or something like that. Alex Kurakin found that if he printed out adversarial examples and then photographed them with an Android phone, they would actually still fool the classifier in the Android phone. They're robust enough that they can survive the changes in lighting and viewpoint and imperfections in the lens, JPEG compression in the camera app, that kind of thing. So you can actually go out and fool entities in the real world with this. This has been a point of ongoing debate. A lot of people keep adding more criteria that they think we need to find before we be concerned about this. Like, for example, it needs to survive more viewpoint changes. It needs to survive being detected and then by a detector method and then cropped closely and so on. And so there's been a lot of back and forth with a group at UIUC saying, basically you can't really fool a detector in a realistic scenario, and then OpenAI and Berkeley have replied with follow-up papers saying, well, actually, we can fool the classifier in the setting that you requested in your latest argument. Right now, UIUC is the last one to have argued that this is not actually a problem, maybe about a week ago. And I suspect somebody will probably come up with another counter-argument and construct adversarial examples in the latest scenario that they've challenged people to make adversarial examples for. One of the strongest techniques that we have is training on adversarial examples. And for some reason, my slide isn't actually loading here. But if you think of adversarial examples as being like a game, the training process is basically a min-max procedure. The person designing the classifier is trying to minimize the error, and the adversary is trying to maximize the error. So if you train on inputs that maximize the error, you're basically running a min-max problem, much like AlphaGo or any of the other game-playing agents. You're really just trying to find a Nash equilibrium of a game. In practice, that amounts to training on adversarial examples. And for a long time, we found that if you train on adversarial examples, your model will become robust to adversarial examples that were constructed by exactly the same algorithm that you used at training time. This year, that has started to change. Alexander Madry's lab at MIT found that if they add a bunch of random noise to the input before they start running a multi-step optimization process to search for very powerful adversarial examples, and they train on those for a long time, they actually learn a model that is robust to very many different types of adversarial attack. And actually, if we're constrained to obey the max norm constraint that every pixel cannot change by more than an epsilon of 0.3, no one has been able to get the error rate on that model to higher than about 12%, which is very impressive because usually if you used an iterative optimization algorithm, you could get the error rate to essentially 100% on this kind of task. So it seems like we may be close to success on MNIST. We can't prove that no stronger algorithm would break it. One direction is trying to prove that. On larger data sets, it still remains difficult to defend against adversarial examples, even by training on them. One future direction, and one direction that has already started, I should say, is actually verifying these networks to make sure that they treat input points as we would like them to be treated. For example, there's a method called reluplex, where you can prove that all points within an epsilon norm ball of some particular input are classified in the same way. So this doesn't handle generalizing to new test points, but you can designate points and prove that there are no adversarial examples near that specific point. Recently, my colleagues and I ran a competition, mostly run by Alex Kurakin, where we had a Kaggle contest to either create adversarial examples or correctly classify adversarial examples. It was the first time at Kaggle that we actually had users upload executables and run them on Google Cloud rather than just uploading static predictions. So we actually had the people on the attack side of the competition deploying their executables against the people on the defense side of the competition. And that is, the competition has wrapped up now. The final round is still running, so we don't have the results yet, but all the submissions are in. We ran several dev rounds to let people practice before the final round. As of dev round 3, the best defense so far was called Ensemble adversarial training. It was developed by Florian Tramé at Stanford and his collaborators. And the basic idea is to train a model on adversarial examples that come from several different members of an ensemble. So no matter which you use as the model as the source of adversarial examples that you transfer, you can resist all of them. And this ended up being used by all 10 of the top 10 teams as of Dev Round 3. So we expect it will probably place prominently in the final round as well. A lot of adversarial example researchers are inspired by the story of Clever Hans. He was a horse in the 1900s who had been trained to do arithmetic. If you went and asked him a math question like, Clever Hans, what's 2 plus 1? He would go, and everyone would start clapping that he had tapped his hoof the right number of times, and he would stop tapping. And for a long time, everyone believed that he knew how to do arithmetic. His owner was not actually a scam artist. His owner had, just trained him to do arithmetic. He gave him an apple when he got the right answer. And eventually, a psychologist examined him and found that if you took the audience away, and if the person asking him the questions is wearing a mask so he couldn't see your expression, he wouldn't know when to stop tapping. You'd say, Clever Hans, it's 1 plus 1. And he would go, and just keep going, waiting for somebody to clap or give him an apple or something. So nobody in this case was actually trying to fool anybody. Nobody was trying to commit fraud. The trainer was just giving Clever Hans a reward when he did the right thing. Clever Hans was just obeying his reward signal. The audience wasn't trying to give Clever Hans a side channel to answer the question. They were just excited that it looked like he got it right. The same thing has kind of happened with machine learning algorithms. We ask them to maximize the log likelihood of the training set labels, and they find a way of doing that. And it happens not to be one that corresponds very well to reality, but you don't realize that until you put on the mask and start to test them with adversarial examples. And then you realize that they actually have no idea what they're doing. In honor of Clever Hans the horse, we have made a machine learning library called Clever Hans, where you can implement your attacks and your defenses, and you can have standard reference implementations of them. So if you're building a system and you want to know if it's secure, you can test your system on the strongest known attacks. And if you've built a new defense and you want to write a paper about it, you can report benchmark results, knowing that your benchmarks are using the best possible implementation. One thing that's always difficult in adversarial machine learning research is if you have a new attack and you run it and you get a really high success rate for your attack, you don't know if it's because your attack is good or your defense is bad. So using Clever Hans for one side and your research project for the other side lets you know that you're comparing to the same standards as all of the other researchers. So if you have new attacks or defenses you want to contribute to the library, we're very welcome to add you to the standardized suite. And if you're doing research in this area, please be sure to compare to the strongest known attacks and the strongest known defenses. And then finally, here at BayLearn, we actually have a poster. Check out Justin Gilmer's poster on adversarial sphere, which is a place where he has simplified the problem to the point that you can study adversarial examples using theory rather than empirical experiments. And with that, I'm available for questions.
Please.
When you do, thanks. When you do, so when people typically do adversarial training, do you have to sacrifice some generalization accuracy for more robustness to attacks?
Yeah, that's a good question. It turns out that adversarial training is a regularizer. So if you're underfitting, you will underfit more. If you're overfitting, then you will actually reduce the amount that you overfit.
So we should do it anyway, even if...
If you are overfitting. So on ImageNet, we're usually underfitting. And so on ImageNet, we usually lose maybe a percentage point of accuracy when we introduce adversarial training. On things like MNIST or 20 news groups, a lot of those smaller data sets we see a lot in research papers, you can actually get better test set numbers with adversarial training.
Thank you.
Hi. So I just have a question about the differential privacy stuff you talked about earlier. So I guess if we think of the learning algorithm as simply as a mapping from the data set to the parameter values, then I guess what we'd like is to have a mapping that is not invertible. But it seems like if like the parameters and the data set actually have any sort of mutual information, then it's always possible to invert that mapping. So I was sort of wondering if you think, we can ever have a private model.
So there's a trade-off between what we call utility and privacy. Generally speaking, if you want more utility, you have to give up some privacy. But we can actually achieve very good trade-offs. If you look at the paper for the Pate algorithm, we were actually able to get very competitive classification accuracy on a handful of data sets while still providing reasonably good privacy bounds. And we actually, it's a trade-off curve, but also better technologies can push that curve closer to the corner. And we're clearly not as close to the corner as we can get yet. So I actually think that we will be able to provide a good trade-off between privacy and effectiveness. One other thing is there are a lot of theoretical results that say that privacy and generalization are similar. To generalize well, you don't want to memorize specific instances. You want to learn important general patterns. So to some extent, privacy could actually be a good way of regularizing the model. In practice, we've usually found that with the private algorithms we've been able to develop so far, we lose more to underfitting than we gain by reducing overfitting. But in theory, someday we might have an algorithm that provides privacy guarantees and cuts down the overfitting problem a lot.
Thank you.
On the back over there.
Thank you. You mentioned cases where adversarial examples could have implications for security. Have you seen instances where adversarial examples have been used in the real world to jeopardize security?
I've only really studied them in a theoretical context. Some people have told me that they've seen things that are like adversarial examples, but for like NDA reasons, they haven't wanted to tell me the details. I know that this kind of thing comes up in finance, for example. Some of my friends that used to work in the finance industry said that they spent a lot of their time obfuscating their trading algorithms so that other firms wouldn't reverse engineer their trades and fool them into making unprofitable trades. So that's one of the main cases where it comes up. But this is the kind of thing that I think right now mostly happens in kind of an ad hoc manner. Like if you see the way that people try to design spam or abusive comments to get through the filters, they're sort of doing adversarial examples by manual design rather than automated adversarial examples.
I'd ask a very quick follow-up questions. Have you seen similar techniques used for digital watermarking, mixing in information that you actually care about?
Oh, like can you make an adversarial perturbation that's invisible to the human eye but easily recognizable to a machine learning model? Yeah, I mean, there's a whole field called steganography that you could say is similar to that. I've seen the other kind of adversarial machine learning. I've seen GANs used for steganography. I haven't actually seen adversarial examples of this form for steganography yet.
Hi. So most of the examples that you use seem to be around using epsilon balls around kosher examples. Is there also a line of work where we're actually focusing on naturally tricky images? And do you have any thoughts on whether that line of work may also help?
Yeah, there's been less study of naturally tricky images because it's kind of hard to specify which images are both realistic and harmful. I mentioned Jeff Clune has a paper about images that fool models that are not near clean examples. But those images are still not really naturalistic. They're more like geometric patterns and things like that.
So just a quick follow-up. So I was thinking of more around classifiers which have decision boundaries, for instance, where if you had examples close to the boundaries, then epsilon balls would not be kosher. So is there any work where people are looking at that kind of examples also in this context?
So to deal with the boundary problem, we usually just change which norm we use to define the epsilon ball. So like on MNIST, you can define an L2 epsilon ball that's going to cross the boundary, but a max norm epsilon ball would probably not. And I guess there are a lot of people that study things like support vectors and things like that you could consider as being some of the hardest examples to classify in terms of distance to the boundary.
Are there any instance other than vision problems, like audio, for instance, or even NLP?
Yeah, there's a paper from Stanford about adversarial examples for question answering systems, where actually more or less the same thing works on people. You know how when you take the SAT reading comprehension, they put a lot of irrelevant information in the SAT questions, and then they hope that people will pick one of the multiple choice answers relating to the irrelevant information. You can do basically the same thing to machine learning models. They have this example of, they have a passage about football, and then they add a sentence about Jeff Dean, and then the question is like, which quarterback won the Super Bowl in such and such year, and the system they tested said Jeff Dean. Basically, if you make the sentence about the irrelevant information match the structure of the question, then the attention mechanism will latch on to the extra sentence that you added.
Blade Runner.
Yeah.
Please, on the back.
So you briefly mentioned about the ReLU activation function. So I'm interested to know if there's been studies about how susceptible a network is to attack when you change the activation function.
So far, we haven't been able to make it stronger by changing the activation function, and that's definitely not for lack of trying. We've done a lot of different ones. I think in the appendix to Alex's paper about adversarial examples in the physical world, he shows that he got little tiny changes by switching to a new activation function we made up. And that's mostly just in there for trivia. I've done a lot of things like, sigmoids and tanh, they're not significantly more robust than ReLUs. I've done things like in grad school, I had a model called spike and slab sparse coding. I tried putting that in the network, and that wasn't totally conclusive. The adversary can make the network fail to converge in that case. I don't know what happens if you do get it to converge. I've tried things like there's Nicole Rust's model of V1 cortex in the human brain. That used to be a popular thing to study. Like James Bergstra wrote a paper about it at NIPS in 2009. I tried using that for adversarial examples. It made no difference at all. The interesting thing is the Nicole Rust model of V1 works about as well as ReLUs in my experience. So everyone's forgotten about these neuroscience models, but they actually work about the same as the techniques we all use now.
And I guess this will be our last question, because we want to go to the poster session as well.
Thanks. I was curious. So let's say you have a machine learning algorithm, and it gets deployed. You start to see a bunch of test time results that you're seeing degraded behavior, and you suspect that you are the recipient of an adversarial attack. Can you? I don't know if this is considered a counterattack or at least patching your wall. Can you infer what the attacker has, with training data or parameters? Where is the hole in your system that you believe that they have compromised and are using to attack you? So can you react, I guess, or infer what the vector is?
At present, I don't know how I would figure out exactly what they did. Part of the reason is, for most of the models that aren't explicitly defended, you can kind of attack them with just the data. And so a lot of attacks would look the same, regardless of whether they were using only the data or using the parameters as well. My main advice would be to take one of the latest adversarial training techniques and use that to improve the robustness of your model if you think you're under attack. And you might be able to do a few other things like changing your model frequently, and just reducing the amount of points that an attacker could introduce changes into your pipeline. But at the moment, we're not at the point where we can tell you there's some set of best practices, and if you follow them, everything will definitely work. It's not like crypto yet. It's very much the early days of, we figured out what the bad guys can do, and now we're working on the defenses, but they're all kind of ad hoc.
Okay. Thank you very much, Ian.